Good morning, children. Today we're going to start with a new module, that is module 6. That is computer representation of graphs. Okay, how do you represent your graphs internally inside your computer? So for all computer programs which is developed to solve graphical theoretical problems, the input is the graph itself. നമ്മൾ this particular problem എടുത്താലും where graph is said to be involved. Okay. അവിടെ നമ്മൾ എന്തായിട്ട് ഇൻപുട്ട് കൊടുക്കും? നമ്മൾ ഗ്രാഫ് തന്നെ ഇൻപുട്ട് ആയിട്ട് കൊടുക്കുക. The graph can be presented to and stored in a digital computer in one of the following forms. So we'll be studying some of the forms by which you can represent your graph or you can store your graph. Okay, you can represent your graph and store your graph in your computer. Every graph has got its own advantages as well as its disadvantages. ഇനി നമ്മൾ ഏത് ഗ്രാഫിനാണ് നമ്മൾ യൂസ് ചെയ്യണമെന്ന് പറഞ്ഞാൽ ഇറ്റ് വിൽ ഡിപ്പെൻഡ് ഓൺ വേരിയസ് ഫാക്ടേഴ്സ്. ഫോർ എക്സാമ്പിൾ നമ്മൾ ഏത് പ്രോബ്ലമാണ് കൺസിഡർ ചെയ്തിട്ടാണ്, കമ്പ്യൂട്ടർ ലാംഗ്വേജ് ഏതാണ്, പിന്നെ നമ്മൾ യൂസ് ചെയ്യുന്ന ടൈപ്പ് ഓഫ് മെഷീൻ. സോ ഓൺ ദാറ്റ് ബേസിസ് we'll decide which graph do we have to select. So we have some of the graphs we have already studied. Okay, the representation of graphs we have already studied. We'll just mention all of them. So you remember what your adjacency matrix is. Okay, a very quick review of your adjacency matrix. You have most popular form in which a graph is input for a computer program. So you know that whenever we study from data structures onwards, algorithms also, it is the adjacency matrix which is used for representing your graph. And how is it denoted? It is said to be denoted as x of g. It is denoted as x of g. Taking a small example of this, just a recap, you have the vertices A, B, C and D. Okay, if you have like this, what would be your adjacency matrix? Adjacency in the sense x of g, which is said to be what? You have the vertices A, B, C, D as your rows, and also your columns are going to be the vertices A, B, C and D. And you put a 1 whenever a vertex is adjacent to the other. In the case of your A, B, D and C are adjacent to each other, but B, C, D is said to be 1 and A is said to be 0. In the case of your C, it is A and D. In the case of your C, it is A and D. Okay. In the case of your B, it is again A and D. Okay. B is said to be A and D. And what about your D? D is said to be adjacent to A, B and C. D is adjacent to A, B and C. Okay. The remaining areas will be filled with 0. So this is how your adjacency matrix looks like. Now on the basis of this, they have made some statements. Now let us see what the statements is. It is an n by n binary matrix. It is a binary matrix which consists of n vertices. How many vertices? 4. So 4 by 4 binary matrix. Each entry is either 0 or 1. How many bits it will require? It will require n squared bits. N squared bits in 4 vertices are 4 into 4. How many total bits are there? There said to be 16 bits are said to be you have to use to represent this in computer memory. Now imagine W is the word length. Okay, imagine W is the word length. Then each row each row is said to need, this is C. Okay, this is said to be C, n by W words, n by W words for storage. Hence the total matrix needs n into it is said to require n into n by W words. Now how do I explain this? Here it is a very simple example. Consider you have an adjacency matrix. Consider you have an adjacency matrix where you have A, B, C, D, E, F, G, H. Okay, you have 8 vertices. Okay, A, B, C, D, E, F, G, H. 4, 4, 8. Okay, so 4, 4, 8 in the 1, 2, 3, 4, 5, 6, 7, 8. I just randomly put the values. Like that, you are filling it with all the values. I'm not filling it up. Okay. Something like this. You will have for D, E, F, G, and H. Okay. Now, what is the point this particular point says? If you say W is the word length, that is determined by the user. So word length is normally 8 bits avam, 16 bits avam, 32 bits avam. I'll give you an example with for proving this point. If point proved only, I'll say assume that my one word is said to be equal to 4 bits. Okay, one word is equal to 4 bits. അപ്പോൾ ഇവിടെ അവർ പറഞ്ഞിട്ടുള്ള if W is the word length, then each row it needs ceiling of n by W. So how many bits do you have here in a row? You will have etra vertices under atrayum n. So you know that n value here is said to be 8. Okay, what is n by W? N by W is 8 divided by, it is one word. So I'll change it into one word is equal to 4. That is equal to, I need 2 bits. Okay, so it is said to be 2 bits. 8 by 4, I mean it is said to be 2 bits I'll be requiring. Okay, that is for a single row. I can say a single, not 2 bits, I'm sorry, it is equal to 2 words. I'm sorry, it is equal to 2 words. I'll be requiring 2 words for a single row. I'll be requiring 2 words for a single row. Imagine that you don't have 8 vertices. Imagine you don't have 8 vertices. Instead of that, your n value is equal to 7. That is, instead of having 8 vertices, you have 7 vertices. You are having a 7 by 7 matrix. Okay, you have a 7 by 7 matrix. I do the same calculation n by W. That is 7 by 4. What do you get 7 by 4? 7 by 4 approximately you will get the value is 1 by 7. They have said that you have to take a ceiling of it. You have to take a ceiling of it. Ceiling for the upper value you have to take. That is totally how many words should I need? I need 2 words. I need 2 words. Okay, that is what the first point says. That much amount of storage, that much amount of words you need for storage. Now, hence the total matrix. Now, what about the total matrix? Okay, for a single row, if it is n by W, and how many rows do you have? If you have 8 rows, so obviously it is going to be 8 into n by W. So 8 into n by W is 8 into 2. That is equal to 16. Okay, you will need how many words? You will need 16 words. You will need 16 words in this particular example. What about in this particular example when n is equal to 7? It is going to be 8 into, not 8, sorry, n is said to be 7. 7 into 2, that is equal to 14 words. It is going to use 14 words. Okay. Now look into the next point that they are saying. The next point they say is for undirected graph. Okay, for undirected graph, the matrix is symmetric and hence needs to store only the upper right triangle, which needs only n into n minus 1 by 2 bits of a storage. What do you mean by this? ഞാൻ ഇവിടെ എടുത്ത example undirected graph ആണ്. Yes, can you see the matrix of this? The matrix, the adjacency matrix of this. If you see the diagonal element, it is all set to be 0. The diagonal elements are all set to be 0. So how many, if you see here, if you see this part, and if you compare this part, isn't it the upper triangle and the lower triangle? Aren't the same? Aren't they symmetrical? Okay, they are symmetric. The matrix is said to be symmetric when your graph is said to be when your graph is said to be directed. I'm sorry. When your graph is said to be undirected, the matrix is said to be symmetric. So you need to store only this upper right triangle. You just need to store the upper right triangle. And that will need how many bits in total? It will require n into n minus 1 by 2. So that is, you can see here 1, 2, 3, 4, 5, 6. Okay. So what is n into n plus n into n minus 1? That is, you have 4 minus 1 by 2. Okay. So you get it as 2 into 3, that is said to be 6. And here also it is said to be 6. Okay. So it requires 6 bits of storage. That is n into n minus 1 by 2 bits of storage. I hope this point is also clear. The parallel edges cannot be represented. Obviously, a parallel edge only one edge can be represented. That is, there is an edge which exists between A and C can be represented, but parallel edges in information like adjacency matrix. So that was the first way of representing your graph inside your computer. Now let us go over the next example. Now we look into the, before that I would like to prove this particular point. Directed graph in the case how it looks like. Okay, directed graph how it looks like. Same one, I'm going to draw A, B, C, and D. Okay, if I have something like this, what would be my adjacency matrix for this? X of G is equal to, you have your A, B, C, D, you have your A, B, C, D. Okay, this is a directed graph. In the directed graph, you will see you have an edge from A to B and you have an edge from A to D. So B and D remaining is going to be 0. What about your B? You have an edge from B to D alone. So that is going to be 1. It's all going to be zeros. What about your C? C has an edge going to A and also to D. C has an edge going to A and also to D. So that is 0. What about D? D has no and there's no outgoing edge, so it's all zeros. So if you see the diagonal value, okay, is it symmetrical? Is the left one symmetrical with the, I mean the top triangle and the bottom triangle, are they symmetrical? They are not symmetrical. That is why they said that for an undirected graph, this particular condition is said to be there. Now next we look into the incidence matrix. Also, you have studied what incidence matrix is. If you take the same example, A, B, C, D, okay, and I call this as E1, E2, E3, E4, and E5. What is my incidence matrix? Occasionally, incidence matrix is also used for storing and manipulation of graphs for computers. It is denoted by A of G, okay, and what is the binary matrix consisting of? It consists of n by e. Okay, it is consisting of n by e, where n is the number of vertices and e is the number of edges. So A of G is said to be written as, the rows are said to be your vertices, that is A, B, C, D, and your edges are going to be E1, E2, E3, E4, and E5. You have to remember that we cannot use self loops in case of your incidence matrix. Okay, incidence matrix self loop permit cheyadilla. Now in this case, which all you have to see which all edges are incident with A. A is incident with E1, E4, E5. E1, E4, E5. What about B? It is E1 and E2. What about C? It is E4 and E3. What about D? It is said to be E2, E3 and E5, isn't it? So remaining portion I will put it as 0. So remaining portion I will put it as 0. Okay, so I've got my incidence matrix also, which is said to be n by e. It is a binary matrix. Each entry is going to be either 0 or 1. It requires how many bits? It requires n into e bits, isn't it? How many edges do we have? E is said to be equal to 5 and n is said to be equal to 4. So 5 into 4 is said to be equal to 20, isn't it? If you count here, a single row consists of 5 elements, and how many rows do you have? 4. So 4 into 5, how many of them are there? Yes, it will be 20. Now, how many words of memory? നമ്മൾ നേരത്തെ പറഞ്ഞ പോലെ തന്നെ ഇവിടെയും നമുക്ക് എത്ര words of memory വേണ്ടി വരും? That is n into e, okay, divided by w. That is for a single row. For a single row, എത്ര ഉണ്ട്? Divided by what will give you the words of memory which is required for representing a single row, and for number എത്ര rows ഉണ്ട് full matrix represent ചെയ്യാൻ വേണ്ടി you will have to write n into e divided by w, the lower C, I mean the floor. Now usually the number of edges will be greater than n. Okay, so in that case the number of edges, okay, n into e, here the n into e value is what is said to be 20. It is said to be greater than n into n. What is the value of n? It is said to be 4, isn't it? 4 into 4, what is 4 into 4? It is said to be 16. Which implies that your incidence matrix, it requires more space than your adjacency matrix. Okay, so here the point which it is because it is n into e, right? Extra bits when you know 20 bits in the now in case only 16 bits. A of G requires 20 bits, whereas X of G requires only 16 bits. So you can say that your adjacency matrix requires less space when compared to your incidence matrix. I already told you നമ്മൾ ഈ representationൽ self loop നമ്മൾ യൂസ് ചെയ്യാറില്ല. പിന്നെ എവിടെയാണ് ഇങ്ങനത്തെ ഇൻസിഡൻസ് മെട്രിക്സ് യൂസ് ചെയ്യാൻ പറഞ്ഞാൽ ഇലക്ട്രിക്കൽ നെറ്റ്വർക്ക്സും സ്വിച്ചിങ് നെറ്റ്വർക്ക്സും യൂസ് ചെയ്യാറുണ്ട്. Next, we are going to study the third type, that is what we call as an edge listing. The third type we are going to study is edge listing. So edge listing, it's a very convenient form for inputting a graph into a computer by retrieval, storage and manipulation. But the retrieval, storage and manipulation becomes difficult. ഏറ്റവും നല്ല രീതിയാണ് ഏറ്റവും എളുപ്പത്തിൽ നമുക്ക് റെപ്രസെന്റ് ചെയ്യാൻ പറ്റും. റിട്രീവൽ ഇച്ചിരി ഡിഫിക്കൽട്ട് ആണ്. യു അണ്ടർസ്റ്റാൻഡ് വൈ ഇറ്റ് ഈസ് ഡിഫിക്കൽട്ട്. ഓക്കെ, മാനിപ്പുലേഷനും സ്റ്റോറേജും എന്തിനാണ് ഡിഫിക്കൽട്ട് ആയിട്ട് കൺസിഡർ ചെയ്യുന്നത്? ഓൺലി വെൻ യു അണ്ടർസ്റ്റാൻഡ് വാട്ട് എഡ്ജ് ലിസ്റ്റിംഗ് ഇസ്. Every edge is listed one by one as an ordered pair of vertices. Each edge is represented by its terminal vertices. Now, it is a very big example. Okay, so first we'll see this big example, or I'll take a small example first. Consider that you have V, U, V, W, okay, and Z, okay, something like this. And you can say that these are the edges. You can have A, B, C and D as your edges. Okay, so what do you mean by edge listing? What do you mean by edge listing? Edge listing parna number first of all number vertices edana U, V, W, Z. Okay, so I'm going to have an edge listing. I'm going to have an edge listing. So which all edges do I have? I can just see that there's an edge A, there's an edge B. Okay, then I have C and I have D. I've written it because A, the starting edge is U. So the starting edge of A is said to be U and the other edge is said to be V. So this is a pair. Okay, this is a pair. Okay. Now next for B, you will write it as VW. Okay. Now for C, you will write it as the first vertex is W. You will write it in terms of W. It's said to be WU. It is said to be WU. What about Z? What about your D? It is going to be ZW. It is going to be ZW. So you have done an edge listing. A ki vendi this is vechitte. This is the second one. This is the third one. This is the fourth one. So these are the edges. You don't write it as A, B, C, D. Instead of that, you will write as a pair. Every edge is listed one by one as an ordered pair of vertices. As an ordered pair of vertices. Each edge is represented by its terminal vertices. Okay, over edge and the terminal vertices represented. So you can see that you have an array, okay, where each element is said to be a pair of vertices. Each element is a pair of vertices. Now, if the graph is said to be directed, if a graph number directed only, the position of the vertex in a pair is significant. Okay, the position of it. Just the basis. If I have something like this, okay, if I have something like this, okay, when I write for the edge A, I have to write U, comma V, okay, because U is my head and V is my tail. Now what about C? I'll write it as U, comma W. I cannot write W, comma U, okay, W, comma U in tail. Now what about my B? I'll have to write it as V, comma W, because V is the head and W is the tail. Okay, and then you have say D. Okay, in the case of D, you will write it as W, comma Z. You cannot write it as reverse. Okay, that is how you have to remember in the case of your edge listing. Now again, in this also you have certain points which says that if B bits are required to label n vertices, then you need 2 into E into B bits would be required to store the edge list. Okay, in the case of your example, how many vertices do I have? I have 1, 2, 3, 4. 4 vertices. I say my B value is at B1. That is 1 bit is required to represent 1 vertex. Please remember, 1 bit is required to represent 1 vertex. Now what condition have they said? They have said that B bits are required to label n vertices. Then 2 into E B bits would be required to store the edge list. Edge list space 2 into E into B. So how many number of edges do I have? 1, 2, 3, 4. So that is equal to 2 into 4 into 1. That is equal to 8. So if you see the edge list itself, A ki vendi edges vertices use cheyali 2. B ki use cheyali 2. C ki use cheyali 2. D ki use cheyali 2. So total has how much? 1, 2, 3, 4. 4 into 2 is said to be 8. So you require 8 bits for representing your edge list. You require 8 bits to represent your edge list. Now next is saying that 2 into e into b is less than n squared. So your if you have n is said to be 4, okay, so n squared is obviously 16, okay. And here in this example, I have 2 into e into b, which is equal to 8. Okay. So in this condition, my 8 is not less than 16. 8 is not less than 16. But you can have graphs where the number of bits, the beta value nyan to the 1. Okay. Instead of taking 1, had I taken it as say 3 or something, 3 bits are used here in the 3 are used here in the value in the marum. That is the number of edges were 4, isn't it? And then 3. So that would have become 4 2s are 8, 8 3s are is said to be 24, isn't it? So that is said to be 24 is said to be what? So 24 becomes greater than n squared, isn't it? So they're saying that when you have such a condition that is 2 into e into b. So here in the first case my b value was 1, so I got the value as 8. When the b value became 3, the value increased. So on the basis of b, your 2eb value is going to vary. So whenever you have 2 into e into b less than your n squared, then the edge listing is considered to be more economical in terms of storage than your adjacency matrix. So it depends on number of bits that you use to represent your vertex. So in this case, your 8 is said to be less than, 8 is said to be less than 16, yes. So you can say that my edge listing is considered to be more economical when compared to my adjacency matrix. My edge listing is considered to be more economical than my edge listing. But in this case, where the number of bits to represent my vertex has increased from 1 to 3, the value becomes 24, and 24 is less than 16, no. So in that case, my adjacency matrix is considered to be much better when compared to the edge listing. Okay. Now, for a graph whose matrix, you can have the adjacency matrix is said to be sparse, edge listing would be more efficient. Okay, what do you mean by sparse? Sparse in the sense it has more number of zeros. Okay, so in that case also your edge listing is considered to be more efficient. And in case of your edge listing, you can obviously represent your self loop as well as the parallel edges. So the self loop on the parallel edges on the represent by using the edge listing. So that was the third type of representation. The next, the fourth type of representation is said to be two linear graphs. The next one is said to be two linear graphs. And what do you mean by two linear graphs? It is very similar to the edge listing. Okay, heads of all the edges are grouped as the array, and tails of all the corresponding edges are grouped as another array. Okay, and the ordering of the edges must be the same in both. For example, if I take the previous example, that is U, V, W and Z, okay, and I call this as A, B, C and D. So I'm going to have two arrays. I'm going to have, this is one array and this is my second array. I have to just see that I'm maintaining the same position, 0, here it is 1, 2, here also 1, 2. So for A, I'm going to have it as UV. So U will be stored here and V will be stored here. For B, it is said to be VW. So V will be stored here and W will be stored here. For C, it is said to be UW. Okay, so U will be stored here, W will be stored here. What about your D? D is said to be stored as WZ. So W will be stored here and Z will be stored here. So you can see that you are using two linear arrays. Okay, the starting vertex is represented in the first array and the corresponding ending vertex is to be represented in your second array. So this is considered as one edge. This is considered as another edge. This is your third edge and this is said to be your fourth edge. So I hope you have understood how the edges can be represented by making use of two linear arrays. The storage is the same as edge listing. Okay, obviously 2 into E into B. Etra number of namki 4 into 4. So totally B and the value 1 aanengi namki etra vendi varum 2 into 4 into 1, that is to be 8 bits than namku vendi. Even namku self loops parallel edges namku represent cheyan pattum. You just have to understand the concept. What do you mean by two linear arrays? But graph thanittunnengi adine rendu അതിനെ എങ്ങനെ നമുക്ക് രണ്ട് ലീനിയർ അറേസ് വെച്ച് റെപ്രസെന്റ് ചെയ്യാൻ പറ്റും എന്ന് മാത്രം മനസ്സിലാക്കിയാൽ മതി. Now next type, that is the fifth type that you have, it is said to be called as the successor listing. The fifth type that you have is said to be called as the successor listing. Now in the case of successor listing, how do we do it? Successor listing, it is considered to be the most efficient and frequently used method where the ratio of the number of edges by the number of vertices. Please remember, the ratio of number of edges by number of vertices is not that large. So you're going to employ n linear arrays. നമുക്ക് എത്ര vertices ഉണ്ട് അത്രയും linear arrays നമ്മൾ യൂസ് ചെയ്യാണ് for representing each of your vertex. The first element of your kth linear array is k itself. Okay, ഇപ്പോൾ നമ്മളിപ്പം first array ആണെങ്കിൽ അത് first vertex ആണ് represent ചെയ്യാൻ പോണേ, and അതിന്റെ first element of first vertex തന്നെ ആയിരിക്കും, and the remaining elements represent the immediate neighbors of vertex k. So which all are the immediate neighbors of vertex k? അതായിരിക്കും അത് കഴിഞ്ഞിട്ട് അതിന്റെ successor ആയിട്ട് വരുന്നത്. So let us see an example to understand what the successor listing is. Imagine you have the same. I'm taking the same example so it is quite easy for you to comprehend. So I've got U, V, W, Z. Okay, this was A, B, C and D I had. Okay, now in the case of successor listing, how many vertices do I have? I have n value is set to be equal to 4. So that means I'm going to have how many arrays? I'm going to have 4 arrays. I'm going to have 4 arrays. Okay, I'm going to have 4 arrays. Okay, now this is for vertex U, V, W and Z. And we have said that the first element of the kth linear array is k itself. So U ആണെങ്കിൽ അതിന്റെ first element U ആയിരിക്കും, V ആണെങ്കിൽ അതിന്റെ first element V ആയിരിക്കും, W ആണെങ്കിൽ W ആയിരിക്കും, Z ആണെങ്കിൽ Z ആയിരിക്കും. Okay, that is done. And after that, what you have to remember is the remaining elements represent the immediate neighbors of vertex k. So U and the immediate neighbors are V and W. So we will write V and W here. What about your V? Immediate neighbors are said to be U and W. I'll write it as U and W. What about W? It is said to be U, V and Z. It is going to be U, V and Z. Okay. What about Z? It has got only W. So I'll write only W. So this is how you represent your successor listing. This is how you represent your successor listing. Now let us look into the next point. For undirected graph. Okay, I have taken an example of an undirected graph. In the case of an undirected graph, each edge appears twice. Each edge appears twice. So let us see the first edge, that is UW. Okay, UW. You have UW here. Okay, and then the first vertex, first vertex U ആയിരിക്കണം അല്ലെങ്കിൽ W ആയിരിക്കണം, അതാണ് നമുക്ക് വേണ്ടത്. Okay, so in this case also you have UW here. So it has appeared twice. Okay. Now next is said to be you have UV. What about UV? You have UV here. Okay, you have UV here. So that has also appeared twice. Now next you have this thing VW. What about VW? VW ആവുമ്പം VW ഉണ്ട്. Okay, VW ഇവിടെ ഉണ്ട്. So I can say 2. Okay, now which is the next one that I'm left with? I'm left with WZ. I'm left with WZ. So I have to see here WZ under and ZW under. So I can say 2. So in the case of an undirected graph, each edge appears twice. Each edge is said to appear twice. Okay. Now if B bits are required for naming n vertices, if B bits are required to naming n vertices, and DAV represents the average degree of vertices, and DAV represents the average degree of vertices, then what is the storage that is required by the successor listing? It is given as n into 1 plus DAV dot B bits. Now to prove this point, I'll take us using the same example I'm going to show you. Now what is the degree of U? What is the degree of U? It is said to be 2. Now what is the degree of V? Degree of V is said to be 2. What is the degree of W? It is said to be equal to 3. What is the degree of Z? It is equal to 1. Now what is your DAV? It is the average degree of vertices. That is 2 plus 2 plus 3 plus 1 divided by 4. I get it as 2. Okay. Now, what is the storage? I say the number of vertices is said to be 4. The number of bits required is said to be 1 for representing each vertex. അങ്ങനെയാണെങ്കിൽ എനിക്ക് സ്റ്റോറേജ് എന്ന് പറഞ്ഞാൽ n into 1 plus DAB into B bits ആണ് വേണ്ടത്, which is equal to n is 4 into 1 plus DAB എന്ന് പറഞ്ഞാൽ 2 into B, which is said to be 1 bit. So that is going to be what? It is equal to 4 into 3. 4 threes are, that is said to be 12. Okay. You're assuming that each one of them requires only 1 bit. ഓരോ വേർട്ടെക്സിന് ഓരോ ബിറ്റ് ആണ് വേണ്ടത്. അപ്പോൾ ഇവിടെ നോക്കുമ്പോൾ 1 2 3 4 5 6 7 8 9 10 11 12, isn't it? So നമുക്കിപ്പം എന്തായി, എത്ര സ്റ്റോറേജ് വേണ്ടി വരും? We require only 12. അതേപടി നമ്മൾ ഓരോ വേർട്ടെക്സിന് 2 ബിറ്റ്സ് വെച്ചാണ് റിപ്രസെന്റ് ചെയ്തിരുന്നെങ്കിൽ 12 into 2, that is 24 bits. It is proved. Okay. So I just wanted to show you that point. That is n into 1 plus DAV into B bits is said to be required as a storage. Now what is the last point that they are saying? If one word is said to be, instead of B bits, if one word is required for each vertex label, അപ്പോൾ നമ്മൾ എന്താണ് ബിന്റെ പകരം നമ്മൾ എന്താ എഴുതുന്നത്? n into 1 plus DAV words ആയിരിക്കും എഴുതുന്നത്. When you have to represent it in bits, you have to specify that particular word or word എത്ര bits ആണെന്ന് വെച്ചിട്ടാണ് നമ്മൾ കാണിക്കുന്നത്. That is the only difference that we have. Now, successor listing is said considered to be more efficient than adjacency matrix itself if this particular condition is said to be satisfied. That is, your average, your degree of vertices is said to be less than the seal of n by w minus 1. If this condition is satisfied, then we say that the successor listing is considered to be more efficient than your adjacency matrix. Now, where do you use your successor listing? It can be used for path finding algorithms, and it can be also used for your DFS. It is used for your path finding algorithms as well as your depth first search algorithms. Okay. The traversal algorithms,